Saxon Advanced Mathematics, Lesson 83. Oh, you get to put your brain into a relaxed math mode. This is not a rigorous lesson. This is a rehash of some probability topics that we have had in Algebra 1 as well as Algebra 2, and I'm pretty sure this is the same material as you've seen before. So you probably won't remember it because we don't use it that much, but we don't use a lot of probability calculations in an ongoing basis. But as I explain this to you, you're probably going to be like, oh yeah, I remember this. All right, probability is a measure of statistics, and it is really best applied to games of chance, where we are repeating an action over and over with exactly the same odds of certain events happening, right? When you flip a coin, you're either going to get a heads or a tail every single time you flip it. Human beings don't respond in such predictable ways, so that's why it's really related to games of chance and not like, you know, if you walk down the street, will you meet a dog or a cat? It's games of chance that we are really studying when we are talking about probability. And I think that makes them fun because they're very controlled settings. So let's remember that the probability of any particular event, let's just write event in there. We put in a letter that just reminds us of what we're talking about. Probability is always equal to the number of desired outcomes expressed in a fraction over the number of total possible outcomes. So for our purposes, we're going to express probability as a fraction. And the classic example is if we're flipping a coin. That's the easiest probability event to study. Okay, so let's say we want to know what's the probability of getting heads when we flip our coin. The probability of heads is measured at the number of desired outcomes. It's only one. Getting heads is the only one. The number of total possible outcomes when you flip a coin is 2. Heads or tails, right? Those are the possibilities, but we succeed in whatever this event is only if we get heads. So these are the desired outcomes. These are the total possible outcomes. That's how we get the numbers. Easy, right? Let's amp it up a bit. Example 83.1. This time we're moving on to dice. Now you know that a die is a cube, and it's got 6 sides, as all cubes do, and every side has a number on it expressed with dots, right? Now, imagine a game that you play where you use 2 dice. I'm looking at my new backgammon board. Backgammon uses 2 dice. Monopoly uses 2 dice. The game of life, Clue, I'm pretty sure those all use 2 dice. So that's a pretty normal thing if you're a board game player at all. And so we're going to answer some questions about the probability of getting certain throws when we're using dice. Now, in order to understand all the possible outcomes and even the number of desired outcomes, sometimes we have to draw a map, right? We didn't do it for the coin because you and I can imagine a coin really easily. Doesn't matter if it's an American coin or the coin in a different country. All coins work the same. They have 2 sides. In the US, our coins have heads and tails. In Canada, they have heads and tails. I've been to other countries that don't necessarily have heads or tails on their coins, but I think you can probably translate. You know, there's 2 different sides to a coin. But let's consider the topic of rolling a pair of dice. along this edge, I'm writing down the possible numbers you might roll on one of the die. Die is singular, dice is plural, right? So if you roll just one, these are the 6 different options. But we're not rolling just one. We're rolling 2. So along here, 2, 3, 4, 5, 6. Okay, so this is one of the die. This is the other die. You roll them, you throw them, and then you'll get one number on each. You add them together, and then that's how many jumps you get to take, right? So if you roll a 1 and a 1, then you get to move 2 spaces. If you roll a 1 and a 2, you get to move 3. A 1 and a 3, you get to move 4, and so on. You see the pattern, right? So we're gonna fill in this chart because that shows you the total of the 2 die, and that's what we're gonna be interested in. I'll read you the question in just a minute. I know I haven't even done that yet. I'm so excited about this chart. 2 plus 1, that's 3. Okay, so you're making this chart with me, and we can see it's pretty easy to fill in these numbers, right? You're just adding, and it follows a really strong pattern, right? So we're just filling this puppy in, being thankful for a really easy lesson. 5 and 1 is 6. Oh, sure beats like taking a logarithm of and all that other crazy stuff we've been doing, right? All right, so this is a map of all the possible outcomes you can get when you roll a pair of dice. Now let's see what John has to ask for us. What is the probability of getting a 7? Okay, so this is part A. He's doing that A and B thing. He wants to know what's the probability of rolling a 7. So I get to write this however I want. That helps me. The probability of getting a 7 equals, okay, well now our map comes in handy because we can't just imagine all the different combinations that would give us a 7. We need to really see this all laid out. So I just circled all of the 7s. There are 6 of them. 6 desired outcomes over how many in all? Well, that's 6 times 6, that's 36. So the probability of rolling a 7 is 1 over 6. Make sense? We reduce the fractions when we can. All right, what's the other question that John has for us? What's the probability of rolling a number greater than 8? So the probability of rolling greater than 8, I'm just gonna switch to a different color so that you can see it more easily. Greater than 8, that means 9, 10, 11, or 12. 9, 10, or 11, 9, or 10, 9. Okay, so that's greater than 8, not including 8. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we can simplify this. Let's see, we can take 2 out of both of them. It would be 5 out of 18. That's the probability of rolling a number greater than 8. And this is the correct answer here. I'm pretty sure this is the exact same problem that John uses in all 3 levels of algebra. So if this looks familiar to you, yeah, there's a reason. But again, the secret to doing this problem for doing probabilities when you're rolling 2 die is you have to draw the map. Rolling 2 dice. Okay, that's what triggers this map. Okay, let's see what else John has up his sleeve for us. All right, now he wants to talk about independent events. He wants to talk about the fact that when we flip a coin, every single time we do it, the odds of flipping heads are 1 out of 2. Every single time. If we get 6 heads in a row, that does not change the probability of getting another head. It doesn't make it less likely. It doesn't make it more likely. Every single time we have a 1 out of 2 chance of flipping a head. So John asks, he wants to just sort of nail down our thinking in this topic of independent events. And what I would say about this, the important thing to remember about independent events is that past outcomes do not affect probability. All right, so I'll just keep that in mind. All right. Now, sometimes we want to study multiple events, not to say that it affects the probability, but to say, for example, in this first one, a fair coin is tossed 3 times. What's the probability that it comes up heads every time? So this is what's the probability of getting, this is how we usually write it, heads, heads, heads. And what we're going to do is we're going to look at the 3 different events and say, okay, what's the probability of getting heads this time? It's 1 out of 2. What's the probability of getting heads this time? 1 out of 2. What about here? 1 out of 2. So the probability of getting heads, 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 we multiply them together. And that becomes 1 out of 8. All right, now, this is not the same thing as saying I rolled heads twice. How does it affect my third roll? This is saying, what happens if we do it 3 times in a row? What are the odds of getting that? And so we recognize that they are independent events, but we can calculate the probability of multiple things happening. And let's do one more. A fair coin is tossed 4 times, tossed, not cost. It's tossed 4 times and it comes up heads each time. Past outcomes do not affect probability. We brace ourselves for that. Thus, oh wait, what is the probability it will come up heads the next time? Okay, so to contrast it to this situation, we want to know the probability of getting heads the 4th time. Given that we got heads, heads, heads. This problem is fundamentally different than this problem, and I just want to make sure that you see the difference. I would be looking for the twinkle in your eye right now that shows me, yes, I get it, you don't have to keep talking, but I can't see your twinkle, so I just have to say it a little bit more. The probability of getting heads the 4th time is completely unaffected by the past outcomes. I don't care how many times we got heads in the past. We just know that on the 4th one, the probability of getting heads will be 1 out of 2, just like always. This time we're saying, what's the probability of getting 3 heads in a row? This time we're saying we already got heads 3 times. What's the probability of getting it the 4th time? And this one, it doesn't matter. Past outcomes do not affect the probability of the current event. Okay, I hope that's just as clear as mud. Example. A second, let me write this. Replacement. Replacement always brings into mind the urns. We're almost done, by the way. There's 2 more examples. Urns. I love a good urn. An urn, you know, is kind of like a, almost like a vase or maybe a planter. It's a big ornamental object, and it's great for putting marbles in. So these problems involve pulling marbles out of an urn. Let me draw a picture for you, because that's always the highlight of my probability lesson. Oh my gosh, that wasn't very good. Pretend those are symmetrical. Okay, and then here's the top of our urn. It's open, right? So we can put marbles down in here. Now, in our problem, an urn contains 2 black and 2 white marbles. Okay, here's a black, here's a black, here's a white, and here's a white. A marble is drawn at random and replaced. Okay, so we took one and then we put it back. Then a second marble is drawn. A, what is the probability that both marbles are black? So what's the probability of black, then black? Okay, with replacement, which is what John told us we're doing here, the first time, we have 2 desired outcomes out of a total of 4. And we put it back, and so then with our second event, again, it's 2 out of 4, right? And then we multiply these together. We get 4 out of 16, and we reduce that to 1 out of 4. That's the probability of getting a black and a black. But again, that's contingent on the fact that we picked up the marble, we took it out, we looked at it. Look, there it is, my invisible marble. Then we put it back in the urn. We replaced it. What happens, my friends, if we don't? What happens if we put the marble down? Okay, so now we want to know what's the probability of getting a black and a black without replacement. Well, here are our 2 events. In the first one, it's the same, right? We have 2 black ones, 4 in all, so that's 2 out of 4. But this time, we took out one of the blacks and we put it down. Here, we didn't replace it. Now we only have 1 black out of 3 marbles. So that changes the probability. When we do not replace the marble, that changes the mix and changes both numbers in our calculation. Okay, so without replacement, and again, we multiply these and we get 2 out of 12 equals 1 out of 6. That's the probability of getting a black and a black without replacement. So as you can see, the probability gets a lot lower because once you take one of the black ones out, there aren't as many to choose from. It's kind of like eating all of the red M&Ms or whatever color, right? The more you eat of them, the fewer there are to choose. Okay, we have one more problem, and this one has to do with a deck of cards. So, because I don't know exactly how much experience you have with a deck of cards, I'm going to remind you a little bit about how cards work. 83.5. Okay, a deck of cards has 52 cards. There are 4 suits, and those are the shapes, right? There are hearts, diamonds, clubs, which kind of look like dog footprints, and spades, which are upside down hearts with a stem. Okay? There are 2 colors. These 2 are red, these 2 are black. All right, there are 13 cards of each suit, right? They go from ace. Ace usually counts kind of as a 1. Sometimes we use it as a high card, but oftentimes it is used as a 1. and it goes ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it goes to jack, queen, and king. Those are the 13 different cards. Oh wait, there's not a 1. Sorry, what am I thinking? The ace usually takes the place of the 1. Okay, so that means there's 13 cards in each suit. There are 4 suits, 4 times 3, that's 52. There are 2 colors, so that means there are 26 cards of each color, right? 13 of each suit, 2 suits are red, that means 2 times 13, 26 cards. Okay, there's a lot of information about cards. What's our question? 2 cards are drawn from a 52 card deck without replacement. What is the probability that the first one is red and the second one is black? So we're finding the probability of the first one being red and the second one being black. And this is without. I usually use that as an abbreviation for without replacement. Okay, so in the first event, we want to know how many red cards, because that's our desired outcome is red. So we know there's 26 cards of each color, so that means 26 are red, and there are 52 cards in all. We take a red card, and this red card that we drew, and we lay it down. Now, what has happened to our deck of cards? Now we want to draw a black one. There are still 26 cards in the deck, right? We're assuming we drew out a red card. There are still 26 cards in all, because this was the red. I'm going to write it over here. Red over the total. And now this is the black over the total minus the 1 card that we took out here and laid down on the tabletop. We did not replace it. Okay, so this helps you understand how I got these numbers. So this one is not 52 anymore. This is 51. Whoa, crazy, right? So now we're going to multiply these together, and we're going to do a little bit of work just to simplify the numbers here. 26 and 52 cancel. This goes to 1, this goes to 2. I could have done it off this 26, it doesn't matter. But now I'm going to do this 2 on this 26. I'm going to get 1 and 13. So in the end, I'm going to write my answer up here. The probability of drawing a red card and then a black card without replacement equals 13 over 51. Make sure that when you write your answers to these problems, you specify whether it's without or with replacement, okay? Make sure that's clear as you label your answer. Guess what? That's the end of lesson 83. I hope it was relaxing and enjoyable for you. I hope it triggered up some vague memories of happy days in Algebra 1 and Algebra 2. And I hope you enjoyed this little break, because 84, we're coming back with full force to play with trig identities and sinusoids. All right? So this was just a fun little day at the spa for you. Enjoy a nice, relaxing lesson. Okay, thank you, bye.